How do the distinct features in the curves, for example the onset of specific plateaus or the steepness of voltage drops, correlate with the electrochemical behavior of the active non-MnO2 framework? And what does this tell us about the diffusion kinetics and possible phase transitions occurring in the electrode? What experimental methods might have been used to obtain these curves, and how does the analysis of such data, perhaps through differential capacity (dx/d) measurements, aid in understanding the mechanisms that govern the performance of these cathode materials? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How might the lower voltage limit of 1.5 V in the Na/Na2/3 MnO2 system compared to 2.0 V in the Na/Na.6 MnO2 system influence the extent of sodium extraction and the associated capacity? And what role does this play in determining long-term cycle stability or degradation? How do the differences in voltage windows between 2.0 to 3.8 V and 1.5 to 4.3 V affect the identification of redox peaks and the evaluation of potential phase transformations within these materials? And what insights do these observations provide regarding the optimization of battery performance? In what ways can the comparative study of these charge and discharge curves guide the design of future sodium-ion battery cathodes to achieve improvements in specific capacity, rate performance, and overall durability? And what additional questions emerge that could direct further research in this field? Ultimately, how do these detailed electrochemical characterizations inform our understanding of the interplay between material composition, voltage range, and the mechanisms of Na-ion transport in layered oxides, thereby helping to advance the development of more efficient and reliable sodium-ion batteries? How does synthesizing the material at 900 degrees Celsius ensure that its water content is kept below 20 times 10? And what specific mechanisms during high-temperature synthesis contribute to achieving such an extremely low moisture level? In what way does maintaining this low water content affect the crystal structure and overall stability of the material when subjected to electrochemical cycling? How does the charge-discharge performance demonstrated in Figure 3.19b, where the specific capacity reaches 190 mAh(G) superscript 1 in the voltage range of 1.5 to 4.3 V, reflect the quality and performance of the material synthesized under these conditions? Considering that P2, type max Fe.5Mn.5O2 is known to be unstable because of the instability of Fe within the oxide, how does this chemical instability fundamentally differ from the stable behavior observed with Co and Mn? What role does the partial substitution of Fe with Mn as performed by Yabuchi et al. play in stabilizing the layered structure, and how does this substitution enable the Fe superscript 3/redox couple to become electrochemically active in the 3.8 to 4.2 V range? What?